Hello everyone, welcome to my YouTube channel. So in this lecture, I will discuss about the palladium catalyst cross-coupling reaction in the organometallics chemistry. So now I am discuss about the steel coupling reaction. So palladium catalyst steel coupling reaction is the cross-coupling reaction involving the organotin-based reagent and organohalides are referred to as a steel coupling reaction. So here in the steel coupling is the reaction between these organohalides and the organotin-based reagents. So organometallic reagent may be in some cases by completely aliphatic, but the coupling can still occur as shown below. So here this is a classical example where Rx is a organic halide with react with this organometallic tin reagent in presence of the palladium L2 palladium catalyst to form this carbon-carbon bond. So here X may be bromide, iodide, or acetate, or chloride, or R1 may be the acyl, alkaline, aryl, allyl, benzyl, or R2, and maybe alkyl, aryl, allyl, or R3 is methyl or N-butyl. So here this is example of the one of steel coupling reaction. So here benzyl bromide reacted with this organotin reagent in presence of palladium catalyst to form this carbon-carbon bond. So this reaction introduced by the J.K. Stille in 1971 between the stannase and halide or the pseudohalide has very limitation on the R group. The toxicity of the tin compound used and their poor solubility in water due to the low polarity are the main drawbacks of this reaction compared to the Suzuki coupling reaction. This has the limited that is used in the pharmaceutical. So that means the reagent that organo tin reagent is used in this coupling reaction. So the tin toxicity due to the toxicity of the tin, this reaction has limitation in the practical ability in the pharmaceutical company. So unlike the Suzuki coupling, no activation of the organostenyl region is required. So the R group of the halide covers a broad range, but should probably not have the beta hydrogen, as this will initiate the beta hydrogen elimination instead of reductive elimination. So the organostenane, however, can be beta hydrogen present in the unlike in Suzuki coupling, no base is required for this reaction. So a wide range of functional group proline well observed and halide substrate with the NO2Cl, OMe, acetate, acid, and even the CHO groups are tolerated. The presence of AR also does not affect this reaction. So neurotoxins, which are 66667 polycyclic ether skeleton, including 18 stereocenter and a tryne side chain, are isolated from the cultural cell of this modified steel coupling, which additional reagents such as the CuCl, LiCl are successfully applied for the construction of the tryne side chain in the laboratory synthesis of this compound. So the steel coupling facilitates the reaction without protection of 3-hydroxyl group. So the mechanism of the steel coupling has been subjected to detailed investigation. A cyclic transmetallation as an associate process has been proposed, which leads to the exchange of L or R2 for retention of the configuration, and the open mechanism cannot be ruled out, especially for the halide containing complexes. So next, I will discuss about the Kumada coupling reaction. So Kumada coupling or the Kumada-Koryu coupling is a nickel or palladium catalyst cross coupling reaction between the alkyl aryl phenyl halide or the triphthalate aryl and the aryl alkaline alkyl Grignard reagent. So in Kumada reaction, basically the reaction between the Grignard reagent and between the aryl halides. So which from this carbon-carbon bond, it is nickel or palladium both can catalyze this reaction. So the reaction type was reported independently by two groups in 1972. So here, before that, this is the catalytic cycle for the steel coupling reaction. So here, palladium 0 is the active active form of the catalyst. First, the oxidative addition of this alkyl halide to form this palladium 2 center. Next, the organoctene is coordinated to this palladium center by a 4-member transition state to form this palladium intermediate, and against the reductive elimination of this R1 and R2 to form the final carbon bond is formed, and this active species is degenerative. So here the oxidative addition and reductive elimination is the key step in the stellar coupling, and here the exchange of the alkyl group between this palladium and the steam via the 4-member transition state. So in the Kumata reaction, so this is the example of the Kumata reaction. So here this Grignard reagent PAH and GBr reacted with this vinyl chloride to form this carbon-carbon bond, which is catalyzed by the nickel chloride DQP. And another example is this Grignard reagent reacted with this type of vinyl chloride to form this carbon-carbon bond. So here the stereochemistry, here is a trans, so here also it is trans. The retention of the stereochemistry will occur in this Kumara reaction. So reactivity of these halides follow the order iodide bromide chloride when PD is used as catalyst, where the certain Ni catalyst the order is chloride iodide bromide. So this reaction is important since it gives a excess of styrene compound. Kumata coupling has been developed based on the 2 earlier reports. The coupling of the Grignard region with the catalytic amount of silver halide and the stoichiometric Grignard coupling. So Z alkaline Grignard region couple non-stereospecifically with nickel catalyst, while the reaction is the stereospecific with palladium catalyst. The phosphine ligand also has a stronger influence on the yield. For example, the bidentate ligand generally bear a higher activity than the monodentate phosphine, and the bis diphenyl phosphenopropane is optimal for most reactions. So the palladium catalysts are introduced to this chemistry by the Morossi in 1975. He found that palladium 0, similar to the nickel catalyzed reaction, was able to catalyze reaction with the alkyl and aryl Grignard region with this aryl or alkynyl halides. So in the Kumara reaction also can be done by the palladium. So this is one example where this aryl bromide react with this Grignard reagent in presence of the palladium catalyst to form this carbon-carbon bond coupling product. So and also the in the presence of the phosphine ligand also affects the rate, also affect the rate and the reactivity of the complex. So bidentate phosphine ligand is increase the reactivity and compared to the monodentate ligand. So the application of the Kumada reaction coupling is somewhat limited because of this incompatibility of the Grignard region with certain functional groups. So however, recently the scope of this reaction is extended to aryl coupling with the improved functional group tolerance. So this. So next, I will discuss about the Negassi coupling reaction. So Negassi coupling is a cross coupling reaction that involve an organo zinc compound and an organic halide, and the nickel or palladium catalyst creates a new carbon-carbon covalent bond. So the coupling of the heterocyclic ring is often done using this method. So Negassi reaction is a cross coupling reaction between the organic zinc compound and this organic halide, which can be catalyzed by both nickel and the palladium. So from this new carbon-carbon covalent bond. So coupling of the heterocyclic ring is often done using this method. So the Negassi coupling, which is first reported in 1977, was the first reaction that allowed the preparation of unsymmetrical biaryls in the good yields. The active catalyst in this reaction is the palladium 0, and this reaction is generally proceeds with the oxidative addition of the organic halide, followed by the transmetallization with this zinc compound, finally the reductive elimination. So this versatile reaction has broad scope, is not restricted to the formation of biaryl. Both organic zinc halides, diorganic zinc compound can be used as the starting material. So well-known compound prepared by exclusive use of the Negassi coupling include the pentaferrocyanil cyclopentadiene manganese dicarbonyl and the hexaferrocyanil benzoate. So this is the example of this negative coupling reaction, where this aryl iodide reacted with this organocene in presence of this palladium catalyst to form this coupling product. So the palladium catalyst alkylination coupling under negative condition has been one of the most sought after cross coupling protocol with Suzuki coupling. So negative coupling is often preferred over Stille coupling for alkylination as shown in the following example. So here the negative coupling is preferred over the Stille coupling. So here this is a team reagent, a organoid team reagent reacted with this organoid halide to form this product which is upon the 50% yield of the product. And when this organoid team reagent is converted to the organogene compound and reacted with the organic halide to form this coupling product, the 95% yield of the product. So here the negative coupling is much better than the Stille coupling reaction in terms of the yield of the product. So negative coupling also has an upper hand over the Sonogasera coupling in many reactions. For example, Sonogasera coupling occurs preferentially on aryl iodide, while the aryl chlorides can undergo further alkylation by negative coupling. The cyanuric chloride also undergo alkylation under a negative condition to keep the trialkynyl derivatives. So here first this aryl chloride to from this to make this aryl iodide and aryl chloride. So here this first Sonogasera coupling reaction occurred where this aryl iodide bond carbon iodine bond is activated, not the carbon aryl chloride. So here first this product is formed. Next, this under the Stille coupling condition. So under the negative coupling condition, so first then this coupling product is formed. So here this is the one of the main drawback of this Sonogasera coupling reaction. So where in the Sonogasera coupling reaction, preferentially activate the aryl iodide, not the aryl chloride. But in case of the negative coupling reaction, the aryl iodide and aryl chloride also activated similarly. The mechanism of this Stille negative coupling and the Kumada coupling are quite similar, but both involve the oxidative addition followed by the transmetallation. So this is the example. This is a catalytic cycle of the negative coupling reaction. Here it is the palladium 0 is the active form of the catalyst. So first the oxidative addition of this alkyl halide, aryl halide to from this palladium 2 intermediates. Next the transmetalation between this organotene and this palladium 2 intermediate to from this intermediate. And next here this R1 and R is in the transform. So here this sister isomerism occurred to form this intermediate where the R and R dash is in the cis configuration. Next the reactive elimination to from this R and R dash to form this coupled product, and this palladium 0 is regenerative. So trans is isomerism followed by the reactivation give the coupled product. So the in comparison, some of these reactions under similar condition point to the advantage of the Suzuki method over the Stille reaction, Stille and the negative reaction. So here so in this table, say comparison between this under similar condition, advantage of the Suzuki method or the Stille and negative reaction. So here this aryl halide react with this reagent in presence of the palladium to form this coupled product. So when this X is equal to bromide and this in the under the steel coupling reaction condition, we got the 0% yield of the product. And when this is aryl iodide, in case of steel coupling reaction, this the yield was also 0%. But for in the sodium coupling reaction, for the both the bromide and iodide under the same condition, this quantitatively good yield of the coupling product is observed. And in case of the negative coupling reaction, under the same condition, this yield was comparatively low. So this data conclude that the Suzuki coupling reaction is much more have the advantage over the negative and the negative coupling reaction. So next I will discuss about the Hiyama coupling reaction. So Hiyama coupling is a palladium catalyst CC bond formation between the aryl alkyne and alkyl halides or the cellular halide and the organosilane. So the Hiyama coupling is this mainly the reaction between the aryl halide and this organosilane reagent. So this reaction is comparably to the Suzuki coupling, but it requires an activating reagent such as the fluoride ion or base. The polarization of the SiC bond is important for the success of the Hiyama coupling reaction. Therefore, the first necessary step is the activation of the silane with the base or fluoride ion that leads to the pentavalent silicon compound. So unlike the Suzuki coupling reaction, in this Hiyama coupling reaction, so first due to the less electronegativity difference this carbon and the silicon, the carbon silicon need to be activated first. This is the first step for this Hiyama coupling reaction. So by adding the base or the fluoride ion, that will form a pentavalent silicon compound that they activated the carbon silicon bond. So this reaction rate is also increased by using silane with the fluoro or a toxic group instead of the alkyl. So in fact, there are the only few examples of successful coupling reaction with this trimethyl silane derivatives. So Hiyama coupling were first reported by the Hiyama group in 1988. The reaction on nitronaphthalene with this trimethyl vinyl silane obtained one vinyl naphthalene. The catalyst used as the allyl palladium chloride dimer dissolved in the HMPA and TSF. The reagent used as the fluoride ion source. So here the fluoride ion HMPA or the TSF is act as a fluoride ion source. So organosilane are stable compound with a low toxicity, can easily prepared. So many improvement in this reaction condition have been reported, which has made the Hiyama coupling an interesting alternative for the Suzuki coupling, and it offers a comparable scope for conversion. However, the commercial availability of the boronic acid and boronate currently makes the Suzuki coupling is a more convenient choice. The Hiyama coupling possesses advantages such as low environmental impact, high atom efficiency, safe handling compared to the coupling agent organobone, organozinc, or organotin compound. So the reaction proceeds through the oxidative addition, transmetallization, isomerization, and reductive elimination sequence. So the purpose of the fluoride ion is to activate the conversion silicon compound to the pentacoordinated anion intermediates, which is more amiable transmetallization. Without the added the fluoride, the organosilane compound is simply too stable. The reaction in which the fluoride ion is replaced by the strong base can also be reported for the Hiyama coupling reaction. So this is an example where this organosilicon react with this alkyl bromide to this coupled product. So this is the dialectic cycle for this Hiyama coupling reaction. The first, the 3 steps. One is a 4 step. One is oxidative addition. Then this transmetallization. Next isomerization, and another is the reactive elimination. So first, this palladium 0 is the active form of the catalyst. Upon first oxidation or this aryl halide to form this palladium 2 intermediates. Next, these pentavalent organosilicon reagent did the transmetallization metallization with this palladium 2 to form this. There is the isomerization of this intermediate to form this intermediate where this R and R test are in the 6th position. Then the reductive elimination occurred. to from the final coupled product, and the palladium 0 active is regenerated. So next I will discuss about the Buchwald Hartwig in CN cross coupling reaction. So the coupling of a aryl halide with an amine forms the aromatic amine. So Buchwald Hartwig reaction is the cross coupling between the aryl halide with an amine to form this coupling product to CN1 cross coupled product. So this reaction was made practically by the palladium based catalyst system, was developed almost simultaneously by the Buchwald and the Hartwig. So before their methods, no general reaction for conversion of the aryl halide in the aromatic amines were available. So this reaction has a profound effect on the drug discovery, as many drugs are aromatic amine derivatives. Although initially this reaction works with the aryl bromides and iodide, the use of the bulky phosphine made the reaction work well with the aromatic chloride as well. So this is the example where the aryl halide reacts with this amine to form this coupled CN1 product. So here X may be bromide, iodide, triplet, and R may be the alkyl CN, COPH, and R dash is the alkyl and aryl. So this reaction has been used in the synthesis of many natural products and the nitrogen containing heterocyclic even on the industrial scale. In 1999, Buchwald described this very simple one-for series of indoles using the benzophenol dihydrogen and the aryl halide. Using this protocol, analogous synthesis of the carbazole were achieved by the pharmaceutical company AstraZeneca. The tricyclic indole also is synthesized using this Buchwald Hartwig coupling, which is a precursor for natural products such as the. So this catalytic system contains 4 components to generate the desired CN bond. So the palladium precursor is typically stabilized in the solution by the adequate ligand, which increases the electron density at the metal to facilitate the oxidative addition, and also sufficiently bulky to accelerate the reductive elimination of the product. So as base is required to deprotonate the amine substrate prior to after the combination of the palladium center. So this is the example of this Buchwald Hartwig coupling reaction. So here this amine reacted with this alkyl halide to form this coupled product. This is another example to form this carbazole, between which were one of the key step of this coupling reaction. So this is the catalytic cycle for Buchwald Hartwig CN4 coupling reaction. So here first one step is the oxygen, first step is oxidator addition to this palladium 0 to form this palladium 2 intermediates. Next, this base required to replace this halide with this counter anion to form this intermediate. Next, this amine is did the ligand substitution reaction to form this intermediate. Next, reactive elimination to form this desired coupled product. Solvent also plays a prominent role in this reaction as compared to the other cross coupling process due to the heterogeneous nature of this reaction. It also takes care of the solubilities of the base and the substrate. So variation of this reaction is also available for CO cross coupling reaction. So here with this ligand halide reacts with this alcohol to form this carbon CO cross coupling product. So next we'll discuss about the cross coupling reaction in aqueous media with this functional group product. So water is often sought after replacement of the organic solvent as the inexpensive, non-toxic, and the non-flammable beside allowing easy separation of the organic product from the aqueous biophysical reaction mixture. So the functional group product show in the many pigmented reaction has promoted synthetically chemists to attempt reactions when in the water medium on the fragile biologically important molecule having the host of the functional group. And the important features of this cross coupling reaction conduct in the aqueous medium is requirement for water soluble phosphine catalyst where the palladium acetate PDNO342 work well as the water soluble palladium compound and a variety of phosphine have been synthesized specifically for this purpose. So most of them have been either a sodium sulfonate group or a amine hydrochloride group bound to a distance to trivalent phosphorus center. A list of water soluble phosphate is used in this cross coupling reaction. One is the TBPTS, TBPTS, TXPDS. So this is the water soluble phosphate ligases using in the cross coupling reaction. So interesting result on the functional group proteins have been observed in the synthesis of the non-natural nucleosides. C-modified nucleosides show significant antiviral and anti-cancer activity, and also serves as the model compounds for starting DNA modification caused by the carcinogens in the host of the functional group are present in this molecule, and normally one has to protect them before the serialization is carried out and then reprotected them later. But by using water-soluble phosphates, other TPPTS, TXTPS, decoupling can be carried out without protecting the functional group. Very good yield of the serial nucleotide are obtained. Condition as given below, the reaction can also be extended. The unprotected halopurine halonucleoside, nucleotides, and the nucleoside triphosphate. So while the TPPTS related ligands, so here is alkyl aryl bromide reacts with this boronic acid in presence of water medium to form this coupled product. So while TPPTS and related ligand typically repair aryl iodide or activate the aryl bromide substrate and moderately high temperature by using tert butyl amphos or tert butyl biphos along with the palladium salts. So the Suzuki coupling on unactivated aryl bromide can be preferred perform at room temperature. So this reaction can be carried out in the pure water or water acetonite or water toluene biphasic mixture media. So the added advantage is that the catalyst derived from this TFOS can be recycled up to 3 times without any decrease in the catalytic reactivity. Here and Sonagasilia coupling also possible using the tart butyl amphos at 80 degrees centigrade and 50 degrees centigrade at hours media. So this is the example of the coupling reaction in presence of the water medium. So using the buccal sulfonated ligands, the coupling of aryl chloride in aqueous solvent under mild condition can be carried out. So these ligand can also successfully applied to Sonagasilia coupling or aryl chlorides or bromide and then has the fast catalytic system to a couple of deactivated aryl bromonic and proponic acid. So this is an example where the aryl chloride react with these bromonic esters to form this coupled product in presence of water medium. So next I will discuss about the cross-coupling reaction of the organohalide with non-organometallic and non-heteroatom-based reagent. So there has been also some significant development in the palladium catalyst cross-coupling reaction, where the conventional organometallic or heteroatom-based coupling partner has been replaced with the entirely organic reagent. The most well-known among this section are the palladium catalyst, alpha arylation of the carbonyl compound, and the decarbonation of cross-coupling reaction. So palladium catalyst, alpha arylation of the carbonyl compound. So in this reaction, the enolate coupling partner generated from a carbonyl compound having the sp3 unit and base is required with the aryl halide or CO2 halide in presence of palladium catalyst. So a sp3 coupled product is obtained through the device of SCH1. The palladium catalyst reaction was reported for the first time simultaneously by the Rupert Mibra. The alpha arylation also found to occur the nitrile in place of the carbonyl compound. So this is the alpha arylation reaction of this carbonyl compound. So here this aryl halide reacted with this carbonyl compound in presence of palladium to form this coupled product. So here the alpha arylation at this stage at this alpha carbon of this ketone to form this coupled product. So next one the decarboxylated cross-coupling reaction. In 2022, Myers reported a palladium catalyst reaction in which the decarboxylated cross-coupling was carried out between the aryl carboxylic acid and styrene based on silver carbonate as an added salt. The reaction was later extended to the Gaussian to aryl halide with this CUI and CU catalyst. In 2020, decarboxyl cross-coupling where both coupling partner where carboxylic acid also reported. So this is the example of the decarboxyl reaction of this aryl carboxylic acid and styrene. So here this is the palladium catalyst. The decarboxylate coupling product is obtained. So next I will I will discuss about some problem. So first, in this problem, name the reaction and those are structure of the final product from the following reaction. So here, this react with this moronic acetate in presence of radia. So this is the Suzuki coupling reaction. So where the final product is ONE and ONE. So this is the final product. So this is one of the example of the Suzuki coupling reaction. So next, here this MgBr, this ignited reagent react with this alkyl aryl halide in presence of radium chloride. So this is the example of the Komata reaction. Is the here the coupling between this is occurred from this final coupled product. So next one is this organogene. Reacts with this halide. So this is an example of the legacy coupling reaction. So here this right we replace the couple between this carbon and this carbon is occurred. So next one is the this example of the Kumada coupling reaction is this. There is a Kegnard reagent react to this aryl bromide. So here the coupling between this carbon and this carbon is occurred in presence of nickel chloride. And next question is the give the four basic difference between Suzuki and the Stille coupling reaction. So for the Stille coupling, the alkyl halides should not have to beta hydrogen as it will initiate a beta hydrogen elimination instead of the reactive elimination. So no activation of the organostenol group is required in the Stille coupling. Therefore, no base is required. But where the in case of the Suzuki coupling reaction, the activation of the boronic acid required a base. And third one, the side product from the Suzuki coupling is not toxic. Where it is a toxic in the Stille coupling reaction, therefore the former is preferred for synthesis of the pharmaceutical products. And separation of the organic product from the organostenol is difficult in the Stille coupling, where the boronic side product from the Suzuki coupling can easily separated from the organic product. So next, identify the name and the name of the reaction of the following. Next question is the identify and name of the reaction in the following transformation. So here this for the reaction A, this is a Suzuki coupling reaction where this organohalide reacts with this boronic esters to form this coupled product. So this is the example of the Suzuki coupling reaction. So next one, here this ignited reagent reacts with aryl halide to form this coupled product. So this is the reaction example of the Kumada coupling reaction. So next, the organosilicon reacts with the bromide to form this coupled product. So this is the reaction is the Sonagashira coupling reaction. So here, this is the example of the Suzuki couple by followed by the head coupling reaction. So here the organotene reacts with aryl bromide to form this product. So this is the example of the Buchard-Hartig coupling reaction. And this one, the aryl halide react with this thing. This is the example of the Negasi followed by the egg coupling reaction. So here the aryl organohalide reacts with this organic thing. So here the coupling between this and this carbon occurred. So this is the example of the Stille coupling reaction, and final product is formed between this and this. And here this is the aryl bromide reacted with this in presence of So this is the example of the head coupling reaction. Here this silicon ion silicon chloroanisole. So here reacted is from this. Here this is the example of the hammer coupling reaction. So next question is the highest of reagent and then reactant and reagent to bring out the following reaction. So here this aryl halide reacts with this boronic ester in presence of palladium and phosphine ligand. So this is the cellular coupling reaction, and in this case, this bromide is reacted. So for this boronic ester in presence of this aryl halide, in presence of palladium acetate, and this phosphine ligand, to form this is also a cellular coupling reaction. So thank you.